Hello, welcome. In this video, we're going to be proving Rolle's theorem. Okay, so I think that one thing you need to know about, before I go into this, is the extreme value theorem, which tells us that if f is a continuous function on a closed interval, then it must take both a maximum and a minimum on that interval, right? If it's continuous, it's, I need my actual pen. Continuous on the closed interval, it's got to have a maximum and a minimum. It looks like in this situation, the minimum is here at the left end point. But, it could be a very different scenario, and we could have, the maximum at the right end point and the minimum down here in the interior. It's got to have both, though, because it's continuous. If it was not continuous, you could have no maximum. Or if the interval was not closed, you could have no maximum like that. Okay, but that's kind of getting away from what we're talking about. We're saying that if a function is differentiable and on a closed interval and the values of the function at the two endpoints are equal, then that's evidence of a horizontal tangent somewhere in the interior of that interval. Okay, so let's get. All right, so the first case I want to talk about is kind of a boring case that I'm just going to draw you a picture of. And so, okay, here's f of a and f of b, right? They're equal. And in the case that f of x equals a, which is the same as f of b, right, it's a constant. In the case where f is constant, its derivative is 0 everywhere. So its derivative is equal to 0 for all of the x values between a and b, and so, it's Rolle's theorem is satisfied. So what I'm going to say now is that suppose there's some activity, right? It's not just constant, okay? And if that's the case, then it's either going to have to go up or it's going to have to go down, okay? Now, I'm going to assume that it's going to go up, okay? So that'll be my second case. Suppose f of x is greater than our starting value f of a for some x. For some x between a and b. Okay. Well, because the function is differential, we know it's continuous. Okay, that was one of the theorems that we got in the first unit. Okay, was that differentiable implies continuous. And now because f is continuous on the closed interval, we're going to apply the extreme value theorem and say f has a maximum value on the closed interval a to b. And now I'm going to clear that out, and I'm going to call this maximum, that's happening at x equals c. Okay. I'm going to call it f of c, being the maximum value. And because I've got this up here, this fact that f of x is bigger than f of a at some point on the interior of the interval, that means that this maximum can't happen at the endpoint, right? Because at the endpoints, the y-coordinate is f of a and f of b, which is the same as f of a. Okay, so that means that f of c occurs on the interior of the interval. So if the maximum is occurring at not the edge, then it has to be a local maximum, right? It has to be a situation like that where I've come up and then come back down. Okay, so, and since the value of the derivative at a local extremum is always either 0 or undefined, okay, I know that the differentiability of f throws out the possibility of undefined. Okay, so I'm going to just write, and I'm going to just really emphasize my conclusion, which is because of the conditions of the theorem, because f is differentiable, and still, yep, barely in the shot. Because f is differentiable, undefined is not going to be possible. that means f prime of c equals 0. And like I described, c has to be in the interior of the interval. Okay. So we've shown that f prime equals 0 for some c strictly between a and b, and that's Rolle's theorem.